So we're going to continue talking about the environment where we left off, but instead of talking about temperature, we're going to talk about like humidity and altitude and just the air itself. Okay, so we've got this thing called a psychrometric chart, and it looks complicated, and it kind of is, but it's kind of not. Okay, and so I want you to like not freak out here, okay, but just take a minute to look and see what the variables are. So on what you would normally call the x-axis, you have dry bulb temperature. Okay, so basically think of that as just what's the temperature outside. All right, on the y-axis here, we have the water pressure. Okay, and so I'm going to come back to that. On these curved lines, so I don't know how you describe that, but these curved lines this way, you've got what's called wet bulb temperature. And so that's the temperature of basically something that's fully saturated with water. And then we've got within, excuse me, that's these blue lines here. And then we've got these curved lines, which is humidity. Okay, so let's walk through this for a minute. So again, notice that we've got 4 different colored lines. So we're going to go through this. So wherever you've got these vertical lines, that's where temperature is constant. So here, that's what, 52 degrees Celsius. That's pretty hot. Okay. Here we've got constant water vapor pressure. So in this case, it's 42. Okay. This diagonal line, this is where wet bulb temperature is constant. Okay. And so in this case, it's 25 degrees Celsius. Okay, and then we've got these purple curve lines, which are constant humidity. Now, what's important to know is that dry bulb temperature will always, always, always exceed wet bulb temperature. Okay, and the reason for that is that wet bulb temperature is the temperature of the air when there's, like I said, when we're saturated. Okay. The environment can only, or air can only hold so much water based on the temperature. This is why the summers in Indiana are terrible. It gets hot, which it gets hot everywhere, but it gets really humid because the atmosphere is able to hold a lot of water. Okay, so notice, and the amount, or the water vapor pressure, these aren't going to mean anything to you. You don't hear about this on the news. They just tell you relative humidity. Okay, so at 30 degrees, so we're going to go right here. So 30 degrees, okay, at this point where dry bulb and wet bulb are equal, that's 100% humidity. So in this case, the water pressure is about 32 millimeters of mercury. Again, that doesn't mean anything to you, but what this is saying is that when it's 30 degrees Celsius, the most water that can be held by the environment is 32 millimeters of mercury. Okay, but if we're down here, we'll just say right here, which is about 16. Okay, so in this case, we would be at 50 right here. Right here, we're at 50% humidity. Okay, when it's really cold or when it's cooler, notice that the air can't hold as much water. So when it's 10 degrees Celsius, so that's about what it is. Actually, it's a little warmer than that today. It's what it'll be later in the week. That's 50 degrees. Okay, at 50 degrees, the most amount of water that it can hold is about 10 millimeters of mercury, which is a third. It's a third as much as what can be held when it's closer to 80 or 85. And so this is why when you take a shower in the summer, you get out of the shower, you still feel like you're in the shower because there's all that water in the air. Okay, so what I want to let you know is we will go through this in class. This is one of those things that we're going to go through to help you understand. Okay, the big takeaway right now is that the hotter it is, the more air, or the more water the air can hold. Okay, and humidity, the relative humidity, is just taking the percentage of, well, how much air is, or how much water is actually in the air compared to how much water can the air actually hold. All right, this is why summers suck in Indiana because it's so humid, whereas even though it's hotter in Phoenix, it's much drier because the atmosphere, there's just not water in the atmosphere. All right, so then we've got partial pressure and barometric pressure. So remember, pressure is just the amount of force per area. So we refer to this, or atmospheric pressure is just the pressure of the air. Okay, And so we've talked about this before. So typical pressure at sea level is 760 millimeters of mercury. Sometimes it's referred to as 1 atmosphere, but it's not constant. It can change, okay? And so we can change with high pressure and low pressure systems that you hear about when you watch the weather. It changes with elevation, as we've discussed. The higher up you go in altitude, the lower the pressure because there's less air up there. And this also changes with latitude. Long story short, the rotation of the Earth kind of creates a massive bubble of air around the equator. So there's more air at the equator relative to when you get up closer to the poles. All right, so what's also important to know is that pressure drops with elevation above sea level. We've already know this, but the composition does not. So wherever we're at in the world, this is essentially what the air is made up of. So a bunch of nitrogen, a fair amount of oxygen, and then a small amount of a bunch of other things. Okay, we can use this with Dalton's law, which we have talked about. I know we talked about in 220. So we just take the pressure of oxygen equals the percentage of oxygen in the air times the barometric pressure. Okay, at altitude, barometric pressure is less, and so there's less of each gas. To give you an idea of how barometric pressure changes with altitude, well, let's just look at this. Okay, so sea level, it's about 760. Eugene is slightly higher, and I got this slide from my advisor that was in Eugene. So Eugene and Terre Haute are pretty similar, okay, and so we're still 740-ish, somewhere in there. Notice that when we get to Denver, this is like the bottom of high altitude, okay? So there's the barometric pressure, we're down to about 650, 640. Now, and then we go on so forth to Denali, we're about 380. And we don't even have, and then up at the top here, this is where Mount Everest is. Okay, so on the y-axis on the left, we have the altitude. On the x-axis, we have barometric pressure. And then over here on the right y-axis, we've just got the equivalent oxygen percent. And so what we mean by that is that if we want to simulate what it's like to be on top of Mount Everest without actually going to Everest, we just need to breathe a mixture of gases where it's 6.9% oxygen. Okay, I've done a study before where they had us breathe 10% oxygen, and that was a little uncomfortable, but that's about what it's like on top of Denali. Okay, so basically there's a third as much oxygen in the air on top of Everest as there is here. Total, not percentage. Remember, it's still 21%. Okay, so I want to talk about the ideal gas law, and so we've used this as well. P1V1 equals P2V2. Well, we're going to add a couple of variables. And so what does this all mean? So pressure times volume equals the amount of a gas, so N times a constant, times temperature. And usually this is in Kelvin. So why do we care about this? Well, let's just keep it simple. If nothing else changes but we decrease pressure, that means temperature has to decrease. Okay, so look at it this way. We go on top of a mountain, so if we just go 5,000 feet straight up from Terre Haute, it's going to be colder because there's less pressure. Okay, that's why the tops of mountains are cold. There's less pressure. It used to really blow my mind as a kid because I'm like, we're closer to the sun. You're not that much closer to the sun in the grand scheme of things. We're talking about 93 million miles. Being 5 miles closer doesn't, like, you know, what's the difference between 92,999,995 and 93 million? The answer is very, very little. Okay, but these changes in pressure are quite significant. So if we increase pressure, we're going to increase temperature. Okay, what's also interesting is that if we decrease temperature, we're going to increase density. Again, if nothing else changes. And if we increase temperature, we decrease density. We're giving these molecules the opportunity to try and spread out. All right. And so similar to what we showed you a couple of slides ago, as we, instead of oxygen, we're just going to do with temperature. So this is assuming that we're at the same like latitude or whatever. As we go from sea level to 15,000 feet, notice that the temperature goes from 60 degrees Fahrenheit down to 2 degrees Fahrenheit. Okay. All that's changing is you're going 3 miles up in the air. Okay. So decreased pressure leads to decreased temperature. And with that, we will end our talk about the environment.